Okay, well, thank you for joining us for SLiTHER 55. Our I am recording the presentation for posting later on YouTube, so everybody's got their cameras off except Taylor. Taylor doesn't mind. Um, the Today's presenter is Judith Currano, who is the chemistry librarian at the University of Pennsylvania. She holds bachelor's degrees in chemistry and English from the University of Rochester and a master's degree, I believe, in library sciences from University of Illinois. And she's going to give us kind of an abridged version of her presentation from the ACS meeting, which I found particularly engaging because it's really resonated with me. So with that, I will let Judith go ahead and share her screen and get started.
All right. Hi, everyone. I am Judith Currano. I'm the head of the chemistry library at the University of Pennsylvania. And today I'm going to be talking a little bit about chemical information and artificial intelligence. And the first thing that we might think of when we're thinking about chemical information and artificial intelligence, or any type of information and artificial intelligence, is ChatGPT. And I will say that that will come back to haunt us in a little bit, but I want to focus our attention. We've been talking a lot about AI very quickly in the past year with the rise of ChatGPT. But AI has been present. It's been stealthily infiltrating our information systems pretty much since we started computerizing them. And so I want to focus our attention today a little bit on what's already there, what you might not be aware of, and what you should be focusing on when you're talking to students and when you yourself are using information systems. So the bulk of this presentation was done at the ACS National Meeting in San Francisco. I did add some things to it. So I focused particularly on things I'm doing in class and a few class examples because I thought that would resonate with much of this audience. If you want, this can be very informal. You can interrupt me, raise your hand in the participants, or put information into the chat. And I can address those things while we're going, or I can just go through and then you can ask questions at the end. But to start with, we're going to look at some basic principles of information retrieval. In order to understand how the AI may be helping or hindering us, it's important for us to know what's going on when we search for information. And then we're going to look at 3 different case studies. The first case study is going to be how Web of Science handles an author search using their researcher option. The second is going to be not a case of AI, but a case of database preferences that may be hidden, as we look at how automated preferences can affect a structure search and reaccess. And case study 3, where I can really get down into the weeds if interested, is some text parsing of a test string in 4 different systems. And then after that, we'll look forward towards generative AI and information retrieval and provision. But to start with, here's an oversimplified view of how information retrieval works. So you have a database that contains certain records. It could be substances, it could be article references, it could be a list of author names. And you put some input into this database. If the input exactly matches the content in the record, you'll get a result retrieved. If it doesn't, you won't. So for example, if I type this exact search string into our library catalog, Franklin, I will retrieve this book because you can see the exact words that I typed appear in the book's record. If, on the other hand, I change that input string to artificially intelligent from artificial intelligence, I do not get this book because this book does not say artificially intelligent. Likewise with a structure search. If I chuck this structure of benzophenone into SciFinder and I do an as-drawn search, I will get the record for benzophenone. I will not get the record for benzhydrol because that has a single bond connecting the carbon and the oxygen, and I've drawn a double bond. Now you may be saying to me, well, wait a minute. If I search for artificially intelligent, I will get that artificial intelligence result in some of the systems that I use. And that's because there's some slightly more complicated things going on here. So in many systems nowadays, when you type your input, an algorithm within the database works on that input. It may look up other forms of a word. It may look up other words that could be used to substitute. And then it generates a new search input string that you don't always see. That's what's being searched against the content of the records, and that's what's causing your results. So this is an effort on the part of the information providers to give you more relevant information. What I don't know is what that new input string is all the time. And sometimes those new input strings can result in strange results. Well, this would be nice if this were all that happened, but it isn't. In other search systems, SciFinder, for example, we generate that new input string. We search it against the content in the record, but instead of just returning results, our systems now rank them by relevance, which means the thing that their algorithm decides is the most relevant will fall to the top. The thing that it decides is the least relevant will fall to the bottom. In some cases, it's a simple sort, Web of Science, Scopus. In other cases, though, like SciFinder, they will actually hide some of the records if they do not think it matches a certain threshold of relevance. Well, what is that relevance algorithm? I don't know. I don't know how that's defined. So I would caution people to be very careful, especially if the system seems to be hiding things based on relevance. You want to make sure you can turn that off if you wish. So in general, I like to convey the following to my students. First of all, you can only find information that's published using our information systems. Now we can talk about ChatGPT generating information on the fly later. But for the most part, you're searching for something that's published. And in order to find it, because of that principle of exact match, you need to figure out how the authors express themselves or how the indexers of your database interpreted that information and what additional terminology they may have included. That's going to involve some brainstorming because information systems take you literally. And when they don't, or when you don't think they do, you just don't understand the algorithm. Which leads me to my all-time favorite work-related quotation from J.K. Rowling and Harry Potter and the Chamber of Secrets. Never trust anything that can think for itself if you can't see where it keeps its brain. So the rest of the presentation is going to look at some ways that I've tested systems to see where they keep their brain and how you can apply some of these tests in your classrooms. Before we do that, though, does it matter? As long as the results are relevant, what difference does it make what the system is doing? And I hold it does matter in most cases because here's a very simple example. I ran this search in July. I searched for an author with a unique name. There are no other Judith Curranos out there in the Web of Science. And I got from their researcher search 3 different researcher profiles, 2 of which are well developed and are verified apparently. So does this mean I have a clone? Because I could get so much more work done if I did. Well, no, at actuality, what it means is that Web of Science, I had created a researcher ID. I had then created a researcher ID in the Publons system later. And when Web of Science acquired that information, they acquired my second profile and they just chucked it right into their database. Doing a similar vanity search in SciFinder led to an unrelated problem. Here I started typing my name and I was presented with some options, so I chose one of them. And when I ran my search and analyzed my results by author, I discovered that it had not searched on the string that I input. It had done something else. So we have 3 different Currano J options, one of which does not belong to me. It belongs to one of my cousins. What's the problem? Well, a novice searcher may discard a useful tool if it appears to malfunction in their eyes or if it returns too much junk. And that's why we have to understand the algorithms and try to give our students some tools to deal with them. So the first case that I want to show you is author searching in Web of Science. I wanted to see how well the researcher profiles mapped to the actual work of 27 researchers in chemistry that had a wide variety of areas, publications, years of activity. So I did 2 things. The first thing was I did a researcher search for the individuals in question. If there were multiple profiles, I combined them into a single set. And then I filtered the documents by the researcher's known affiliations to see how good that set was at retrieving only things by my researchers. To see how good it was at retrieving all things by my researchers, I contrasted that with a Web of Science document search, where I searched for the name, either last name, first initial, or last name, two initials, depending on how common the name was, in the author field of the document search. And then I filtered those to the known affiliations. And this is what happened. So you don't have to look terribly carefully at all of these numbers. But what I discovered was that only 3 of the researchers, 2, 4, and 19, had a single Web of Science profile. Everybody else had anywhere from 2 to 4 relevant profiles, including 6 individuals who had gone through and verified their profiles. So that's problem number 1. Now, 5 of these authors, 1, 6, 12, 21, and 23, had profiles that mapped well to their known institutions. In other words, there was a difference of 1 or 2 results when I filtered the documents from their researcher profiles by institution. So that meant that those were pretty good as far as collecting the researcher's work. An additional 10 researchers, if I combined the information, and filtered by institution, I ended up getting good correlation to the results of my manual search. But I had to do that filtering. And here we had a delta of less than 10. So there was less than 10 difference between my manual search and what the automated search presented to me after I filtered by affiliation. In only 8 of those cases, though, were the filtered algorithmic sets identical to the manual ones. In the other cases, they weren't. So that's the good. And you see that there are still several professors that aren't matching up well. And I want to draw your attention to 4 of these. Professors 15, 22, 26, and 27 had serious issues. We're not going to deal with Professor 26. That was a special case. There are actually 2 individuals with exactly the same name, down to the middle initial, who are both chemists. Unfortunately, Web of Science was grouping all of their work together. Fortunately, adding an affiliation filter allowed me to disambiguate those. The other 3 individuals, however, the automated search brought in many fewer than the actual number of publications I had found from a manual search. So I decided to check my work by looking at their publications on their websites, which they obligingly provided. And I discovered that the magnitude of my manual search was much better than the magnitude of my automated search. This is a problem given the way we tend to evaluate our researchers. If you look just at Professor 22's automated search results, their H index is 44 lower than it should be if you look at all of their work. So this is a problem. And it was such a problem that I corresponded with Clarivate to make the Web of Science after doing this research to try to fix some of these issues. So we were able to resolve the issue of my clone because I am the author. They were able to unify that. And now if you search for me, this is what you find out. So that problem is fixed. These problems were a little harder to fix. Again, we didn't even attempt Professor number 26. I focused a lot of information on 22, and we were able to work together to make it so that Professor 22's information, he still has 2 profiles, but now it's doing a much better job of getting all of the relevant results, and it's much more accurate. Professor 15 remains a problem, even after working with Clarivate. One of the profiles that includes this person's work has the wrong first name appended to it, although the professor's actual name is in parenthesis behind. If you omit that, you still get bad results. If you include that one, you're much more accurate. And Professor 27 seems to have gotten slightly worse. So again, a very difficult problem to resolve. And hopefully, as algorithms improve or as individuals take more responsibility for their own profiles, we may be able to see some improvements there. So what do we do with our students? Well, first of all, we need to teach them to be skeptical. The results may seem more precise than they actually are. And we haven't even begun to consider transliteration of author names from other character sets. That's not one that I'm prepared to touch today. It's also important to show the students that what they type may not resemble the actual search run, like my Vanity SciFinder search. I thought I searched on my first and last name. It actually searched on something else. So trying a bunch of different search inputs and seeing what the database does can be very helpful. And manual searching can be a boon if your automated search results, for instance, in Web of Science, are spotty and the precision matters. I actually used this as an activity during my recent classes this fall. I had my students test a researcher versus a document search in Web of Science for an author of their choice, and then compare that to the same two tests run in the Scopus database. And the point of this was to show them that they may need to be critical or skeptical to help them decide which strategy was best in each database and to see the differences in coverage of the two databases. So now I want to change gears and talk about something that's purely a user issue, not an AI issue. And that's an exact structure search for aspirin and reaccess. So I've run this query here. I've drawn the structure of aspirin, asked for the system to retrieve the results as drawn, and I'm surprised to retrieve 950 substances. That doesn't look right. And I can't see what's gone wrong. Well, in actuality, the problem is with the parameters of an as-drawn search. In reaccess, an as-drawn search includes all of these options for tautomers and salts and mixtures and isotopes. And if I systematically uncheck all of these things, then I get to a result that looks more reasonable. I bring this up because when I'm doing a search in reaccess on a wide monitor of a computer, these preferences appear in the sidebar. However, if I'm on a mobile device or if I've minimized the width of my window, these are hidden. And so your researcher, your students may not be aware that there are additional parameters being run, even though in a slightly different environment, they would have been able to see them. So what does this tell us? Well, we need to be alert. We need to know what the search is going to do when we input it. Will it automatically do an exact or a substructure search? That will affect the magnitude of our results. And we want to make sure our results make sense. Does the magnitude match expectations? Do the structures resemble the search input? And if the answer to either of these is no, then we want to learn what might we have done that was unexpected, or what might the database have done that's unexpected. We'll keep an eye on our search parameters. We'll control the ones that we can, and we'll use filters at the end of the search to exclude things we can't control at input. I highly recommend attending trainings, reading documentation, or watching videos to learn tricks and tips. So that brings me to the crux of the matter and the thing that I struggle with the most, and that's topic searching. So topic searching has two problems. First of all, the words I choose to describe my concept may not be the same ones that you would choose. So I have to bear in mind both things. But now the systems are all wanting to behave like a friend of ours over here with a multicolored name. And they're trying to allow you to be perfectly successful with a minimum of training. That means that they're operating heavily on our search input, and that can lead to unexpected results. So let's see what happens when we try Web of Science, Scopus, Google Scholar, and SciFinder topic searches for the string artificial intelligence in chemical information retrieval. So I tried a few tests here. I typed the string just as I have it on the slide, no quotation marks. I tested the string by removing the preposition in and just typing the critical words. And I tested the string putting Boolean operators and or between each of the main search terms to see how that affected it. That was the first thing. So how is it combining the search terms? The second thing I looked at was, are they automatically stemming, auto-stemming, or are they lemmatizing? Reducing the word to a common core and then searching for different variants on that core. And are they using word substitution, where I take a completely different word and substitute it, usually a synonymous term. And then finally, I look to see if exact terms or phrases improved my search. So this is what happened in Web of Science. No matter what I did, I got 8 results. I discovered that Web of Science ignored the word in, and it searched with a Boolean and operator, making sure that all 5 of my words were present in the record. Doing a few searches for different variants on the same word, I discovered that Web of Science does employ some limited lemmatization. So chemical and chemicals brought the same search set. So did retrieve and retrieves, but retrieval brought me a different search set. When I searched for them in quotation marks, that forced the form of the word that I had requested, and in all cases, that was the same. If I tried making phrases to try to get adjacency of my search terms, that led to 0 results. That was not unexpected given the small size of my search set to begin with. So I moved into another system, Scopus, and I did the same tests. So I started out by just typing the search string artificial intelligence in chemical information retrieval. And I discovered that Scopus told me what it did. It put Boolean and operators between all the terms, and it treated the in as a search word. That was interesting to me. It was not a stop word. Doing a couple of other tests, including removing the in, showed me that that was in fact the case. The in mattered here. When I searched for the words to see how it was stemming them, I discovered it was using some lemmatization and searching for simple word variants. Putting a term in curly brackets here, searched for the term exactly as I typed it. Putting the term in quotation marks would search for the term with no word substitution, but would allow auto stemming of the word. And I find that those are definitely very consistent here. Again, using 2 phrases, I could not find any records that had both of these phrases present in the record. Not surprising given the small number of results to begin with. So we moved over to Google Scholar, and this is where things start to get strange. When I type the string with the in, I get 255,000 results. When I leave the in out, I get 271,000 results. So that in has somehow been used. When I do a Boolean and search with Google Scholar says it honors, I get 234,000. So I don't really know what's going on here. It's not a simple Boolean and. When I test my search terms to see if any word substitution or lemmatization is happening, I do find that we are getting word variants. So it is searching on word variants or alternate terms. And when I decide to change the phrases that I'm including, so I do this artificial intelligence without searching for the exact phrase and combine it with chemical information retrieval, again, not an exact phrase. That does change the number of results I get. I don't really understand that. But when I make them phrases, it makes the search set much, much smaller. And depending on how I phrase things, that changes my results. This is the really strange thing. So I discovered this right before the ACS meeting. I was curious because of the difference between these first 2 sets. So I tried for the heck of it, chucking the in at the end of the statement, and was surprised to get a completely different set of results. So last week, I very, very systematically put the in at every conceivable place in the string and got a different set each time. I have no idea why. And the relevance ranking causes not even seeing the same results in all of the cases in the first page of answers. So more testing is necessary. Google Scholar won't let me combine hit sets, so I can't really determine the extent to which these sets overlap or what's being missed. I would approach this one with skepticism. And that brings us to my friend SciFinder. SciFinder is a wonderful, wonderful resource. And the people at the CAS help desk are wonderful, wonderful people and have enabled me to understand how it is parsing search strings as well as anyone can. So taking a look at this, we see that when I type out the string as I would say it, I get 137,000 results. That sounds high given what I've seen in the other databases. When I leave out the in, that raises me to 5 million. That may surprise you. It doesn't surprise me because we had problems like this before. We called the CAS help desk and they told us that when it cannot map the terms to things that are in its master dictionary, it will try to chunk it up and find pieces in the master dictionary, and then we'll employ a Boolean or operator rather than an and to make sure that you're getting everything that's relevant. And what I find is that usually leads to an unmanageable search set. Adding a Boolean and between the terms lowers me to 89 records that have all 5 of these concepts within the same. So again, very complex. I still don't understand the algorithm, not a simple Boolean and, but I've also tested to see if it was a simple Boolean or, and it's not. If I search for any of these terms, I get 16.8 million. If I search for them looking just at the word as typed with no term substitution, I'm still at 6 million. So that doesn't match what I have up here. Trying a few other tests for lemmatization and alternate terminology show that artificial intelligence is treated fairly literally. Chemical information, on the other hand, isn't. So clearly chemical information, we've got some word substitution going on there because it is not a simple Boolean and it is not an exact phrase. When I change the way that I'm searching, and I add phrases in various places, I can drastically affect the number of results that I retrieve. I actually found this to be a decent set, this 4,000 that search for the 2 phrases without exactly quoting them. This one is just a paper that I presented at a past ACS meeting. And this is unsurprisingly the same set that you find up here. So what does this mean for our students? How do we teach them to think? Searching is all about groups and sets. Every term that you input calls a set of records. Terms are not the same as concepts in all cases. And you should make sure that you learn when they are by reading help documentation. So you should think about all potential terms that could describe your concept. And then when you input multiple terms, the system is going to combine these sets in one of several ways. It could intersect them, it could unify them, it could exclude one from another. It's important as much as you can to try to figure out what it is doing. Databases are not all the same. Different databases have different underlying data. I can't compare the results in those 4 databases very well, because I don't know how much relevant information each one of them has in their data set, coupled with the fact that they require different user syntax and employ different levels and types of automated search interpretation. And you'll quickly arrive at the decision that you're going to need to try multiple databases if you're trying to find everything. So I teach my students to test searches for recall and precision. I don't have them do it as systematically as what I showed you, but I do have them run a few test searches to see how the database is interpreting and to read the help files. Learn from your past experiments where alternate terminology seems to get good results, where it doesn't, and to log searches, but be aware that your search may not be reproducible. For these systems that are really heavily working on your search input, those algorithms are constantly changing. Some of them are machine learning based. And so a search I run today may not yield the same results 2 weeks from now, a month from now. So if something looks really interesting to you that you've retrieved, save it. Look beyond the relevance ranking, or at least expand to make sure you're seeing everything. And know when it's good enough. Sometimes I can do a lousy search and that's good enough. I just want to know is something there. If I want to know everything, that's when I have to be more careful. So I actually have my students break down their queries into concepts. brainstorm terminology used when describing each concept, and then choose the terminology from each list that's going to work in the resource they've selected, and structure a query that the resource will understand and that will be effective. And I integrate this into problem sets that I give. So I actually had them take those steps and write it in their problem set so that I could see it. They didn't like it, but it did improve their searching. I also make sure to include some problems that have them compare coverage of databases, knowing that you're going to find different results, but also search in different ways. Although we don't have all the algorithms, we can teach our students to test their queries. So this was the test I showed you before. Adding a third term gives me more permutations that I can check. And again, what this leaves me with is I'm not sure exactly what it's doing. So I know that I need to be skeptical, and I know that I need to try lots of different things to make sure that I am getting everything relevant. I could go further with this and start excluding sets from one another or intersecting the sets to see what's common and what's not, but I decided not to. Let's find out what ChatGPT has to say. So now we're moving into the more modern AI. I asked ChatGPT to build me a Boolean query. I said, hey, I want to find information about artificial intelligence and chemical information. Build me a query. And it didn't do a bad job, but I am really picky. And I looked at this and I said, you've got a syntactic error. The database is going to interpret that space as an automatic Boolean and, or in the case of SciFinder, and I don't know what order it's going to do things. So fix it. And they fixed it by removing the AI term, which I wasn't thrilled about because that could be an important alternate term. Earlier in our conversation, ChatGPT had suggested some pretty good alternate terminology for these concepts. And so I asked it to add that to the query. And it, again, didn't do a bad job for a first pass. So now they've got my AI term back in. They've added machine and deep learning. They've added a few other chemical information. I think these are pretty good, but note that they're searching for all of them as exact phrases. And that might not be the best idea because I could have mining of chemical data, which doesn't actually include the phrase chemical data mining. So I asked it, well, do you know about proximity to search for two terms within a certain number of words of one another? And it said yes, and gave me some examples of proximity operators. I said, great, use them. And it came out with this nonsense. So it did include a proximity operator. It used it in a synonym list. That is not where I would use the proximity operator. I would use the proximity operator between two concepts or between words within a concept. And I certainly wouldn't mix my operators without using parentheses. So I told them it was wrong, and it fixed the syntactic error, but didn't fix the conceptual error. And I decided this was taking way too much of my time. I'm going to build my own Boolean queries. Thank you anyway, ChatGPT. So then I said, well, I'm going to do what everyone else is doing. I'm going to ask ChatGPT just to find the information. And it refused. It said, I can't do that. But it presented me with some not terrible ideas of places to search for information. Wouldn't have been my first choices. And it gave me some pretty good alternate terminology. So I said, okay, ChatGPT, you're a decent thesaurus. Maybe I'll use you this way. So I decided to ask Bard the same question. Could it find me some articles? And it totally hallucinated. It gave me these articles. It described what they were about. But in no case do these articles actually exist. In 3 cases, I can find articles with the same title. In one case, an author actually matches. But 2 of them, I couldn't find anything. And the years were all wrong. This was terrible. So again, at the moment, not what I want. So I decided to check ChatGPT's factual accuracy someplace else. Since it wouldn't give me a list of references, I asked it to generate a biography for me and for my sister, who's a professor at the University of Wyoming. It wasn't horrible, It knew where I worked and what field, that I've won some awards, that I'm with ACS. It didn't know about anything else I was doing besides Penn and ACS. Well, I guess that's all that's important. It didn't know much about my publications or the specifics on the awards. And it gave me a completely different degree granting institution than any I've ever been to, and the wrong fields for my MS, which I guess is better than my sister, where they reported a non-existent MS degree and also got all her institutions incorrect. What's more, they didn't know where she worked, even though she's been at the same institution for a large number of years and has moved from assistant to full professor there. In general, the language was nondescript. The biographies were lacking in detail. I'm not going to have this generate my biography for any kind of grant proposal that I do. But I was curious. So what is the problem? We don't know the underlying data on which they were trained. Bard did hallucinate references. ChatGPT is upfront about the fact it doesn't search, but neither one cited their sources. And unless you know something about what you're asking it, you don't know if it's presenting correct information. And ChatGPT is upfront about this. You should evaluate the accuracy of your output. Okay, so how do we do that? Well, we teach our students to think critically about information. Is it relevant to the need at hand? Does it agree with other information? Is it accurate? Where did it come from? Is it up to date? Is it balanced? Is it biased or slanted? And then information about data integrity and input. I don't have time to talk about this problem with algorithmic biases, but if we don't know the set on which our algorithm was trained, we do not know bias that may be inserting itself into an AI generated piece of writing. So I would be very, very careful in that regard. So this is a technique that a colleague of mine who used to work in Penn Engineering and I developed many years ago to help students evaluate reliability of sources. This is an engineering line diagram. They use it for ethical decision making, and we adapted it for criteria of information evaluation. So for each criterion, we provided a positive and a negative paradigm. And then we had the students graph on the line where they thought the source fell. They did this for the criteria they thought were important. And then they balanced the importance of each criterion to give an overall score. So if authority is more important than timeliness, that would still bump the reliable line over towards the reliable, even though the source may be not quite in date. So to end, AI is everywhere in information retrieval. Whether you see it or not, that's a good thing. I don't want to go back to searching printed chemical abstracts. But we have to remember that these smart search algorithms are not infallible. And there's a lot of places where their desire to help us retrieve something means that we are either thinking we're retrieving everything, but not, or retrieving many things that are irrelevant to our work. So we need to explain the basics of information retrieval. Make sure students know how it works. Make sure they're going to the right sources to begin with, the sources that contain their information. And then think critically about their searches. Don't say, oh, well, I guess there's 5 million results when you've put in a very, very specific query. Think about, why did it return 5 million results? There shouldn't be that much. And that's something that they're going to learn with experience, but it's somewhere we can guide them right now. Chatbots right now make pretty decent thesauri, but really lousy researchers. This may change, but for now, I'm encouraging my students to do their own research. And finally, I'm holding frank discussions with my students about the ethical implications about using AI, about doing a comprehensive background search, making sure people are getting credit when they need to, making sure that my statements are well substantiated, that I'm not wasting time, energy, and money to do research that's already been done or that didn't work the first time. So that's all I have to say. I would love to answer your questions. And thank you for your attention.
All right. Thank you, Judith. I appreciate your frank discussion on search engines because I find so many times, like when I'm in SciFinder, I'll type in a phrase and I get 16 million hits because it has
Yes,
searched every individual word across its database.
it did a Boolean or search
Yeah,
somewhere.
yeah, exactly. So I'll open it up, see if there's any questions from our participants. Um,
I had a quick one.
yeah, sure.
So you had like series of activities for students for kind of interrogating databases.
Mhm.
Have you thought about piecing one together for like, interrogating, Chat GPT and some of these conversational AIs as well?
Not yet. So my course, I should have introduced this earlier. I teach a course in chemical information that's required for the PhD here at Penn. It's elective for BS and MS students. And we focus most of our time on search strategies. And since the chatbots aren't doing search yet, I haven't built any problem sets surrounding that. It's something I'm planning on playing with over the summer. And I happen to have read in a few places that Web of Science and Scopus are actually both planning on including some chat-like function into their database. In fact, one of them, I think Scopus is already beta testing it with some of their institutional subscribers. So as these things hit the search systems, I think it's going to be extremely important for people to test out, like, well, what does it give me if I tell it just a phrase like the Star Trek computer versus if I do the search myself. I'm not sure what that looks like yet, but definitely I would recommend if you want to have your students do this, if there is something that you're learning about in class, if there's something that you're having them research, have them write a paper and then have them tell ChatGPT to write the paper and have them correct its work. I think I saw someone published something like that in JCE, I think, recently. I am not up to date on my chatbot reading. I have a large stack of papers that's waiting for a free moment.
I don't know if I have a question, Judith, but within the Ionic Viper community, we have what we call learning objects that we post online that open source. And I think that this would make your activities would make a great learning object for those of us that are interested in training our students to be better researchers. So I'm gonna plant that seed and follow up with you to see if you might want to do that later on.
Yeah. So one thing that I like to do is I have my problem sets tend to be fairly formulaic in that I decide which skills I want my students to practice. And then the actual searches that I have them run vary from year to year based on their interest. So I think we could definitely set up sort of a framework for testing, and actually something like the Web of Science Scopus author search assignment. I gave that same assignment in a couple of different classes. It was up to the students to choose the researcher. So they were choosing all different researchers. Now I also have a lot of data about what these various systems did with different names and different institutions that I wouldn't have thought about. So yeah, it's pretty easy to build these frameworks that can then be implemented however an instructor might want to in a particular class.
Judith, thank you very much for your presentation.